So heap sort. Heap is a binary tree. Heap is a binary tree where a root node can have at most two children. Any root node can have at most two children. So there is one complete binary tree and there is one full binary tree. Now, what is the difference between two? So complete binary tree, we have a tree like this. This is level 0. This is level 1. This is level 2 for both the trees. Suppose this is tree A and this is B tree. Fine. So again, I'm writing L2 is level 2, L1 is level 1, and this is level 0. Fine. So a complete binary tree is a tree where all the levels except the last level should be completely filled. That means if you see, suppose this is A, B is left child of A, and C is right child of uh, A. Fine. So at level 1, this tree is complete. At level 1, this tree is complete. But at level 0, if I say B has left child E and it has right child F, now this is not complete because it has only left part, but this C tree is not complete. So this is called complete tree. That means we can insert, but the levels are filled. Left and right child are filled. If it is not there, for example, if F child is not there, then this is not a complete binary tree. Now, if I've appended F, that means I can have the space for inserting two more elements with the C. But previous levels are all filled. Supposingly, if this node is not there, then it is also not a complete binary tree. Since C is there, so it is a complete binary tree. And full binary tree means all the levels in a tree should have at most, every node in a tree should have at most two children except the last level. And it should be filled. And it should be completely filled. So it is called full binary tree. It is completely filled, so it is called full binary tree. In complete binary tree, all the nodes except the last level, all the levels except the last level should be filled completely. Whereas in full binary tree, all the levels are to be filled completely. So for this better understanding, I give you one example. Suppose this is a tree. A, B, C, and D. So A is having two children, B and C. So it is complete till level 1. Now this is again incomplete at level 0. Why? Because it is having only one left child, C is having only left child as D, but B is not having any children. B is not having any children. So this is not a complete binary tree. This is not a complete binary tree. Supposingly if E would have been here, now you will say C has two children, but it should be filled from left to right. We cannot fill the right side first before the left child. Fine, so it has to be filled from left to right. It should be filled from left to right. It should not be filled from right to left. It should be filled from left to right. So this is also not a complete binary. Not a binary. Or even if this is not a heap even. Not a heap. A heap is a complete binary tree. A heap is a complete binary tree. See, See, this is a tree, complete binary tree, where I is the parent. I is the parent of 60 and 30. I is the parent of 60 and 30. This is the left child and this is the right child. So left child will be placed at 2 into I position, fine, 2 into parent. That is, if this is at index 1, this would be at index 2. Since I is 1, so left child would be at index number 2. Now, right child would be at 2 into I plus 1. These are very important formulas. 2 into 1 plus 1, it comes out to be 3. That means right child will be placed at index number 3. Left child will be placed at 2 into I, that is 2. And right child will be placed at 2 into I plus 1, that is 3. Next, if I want to know who is the parent of 30, who is the parent of 30, then parent would be at I by 2th index. For example, I want to see the parent of 30. 30 index number is 3. Value of I is 3. 3 by 2, it gives me 1.5. You will are going to take this value. That is floor value. Sorry, seal value. Sorry, you are going to take the floor value. So it will be the parent will be at index 1. That is 50. Parent will be at index 1. That is 50. Parent will be at I by 2 index. Left child will be at 2 into I, that is 2 number, index 2. Right child will be at 2 into I plus 1, that is 3. Then we have parent would be at I by 2th index, 3 by 2, that is 1. Okay, so parent will be placed at 50. Got it? So we have to do the array representation. I tell you how to do this. Suppose these are the arrays A, B, C, D, E, F, and G. We are doing both ways actually. Array representation, tree representation of array, and array representation of tree. We will be doing both ways. How we will be doing? See, 1, 2, 3, 4, 5, 6, 7. Index 1 will be A. Left child is at 2i. 2 into I will be second index, so B. Right child will be at 3 index, that is 3. Okay. Now, who will be the left child of B? Who will be the left child of B? That is 2 into 2 will be 4. So at 4 we have B. Then 2 into I plus 1, that is 5. So right child of B would be E. 3 into 2 would be 6. So left child of 3 would be F. And right child of 3 would be 7. That would be G. Okay. A is 1. 1 into 2 left child is equal to 2 into I. That is 2. Right child is equal to 2 into I plus 1, which is equal to 3. So A's left child would be B and A's right child would be C. Okay. Because it is at index 3. Now at index 4, D would be left child of B and E would be right child of B. Similarly, 3 into 2 is 6. F will be the left child of C and G would be the right child of C, because you have 2 into 3 plus 1, that is 7. So this becomes G. So this becomes G. Vice versa, if we have to do that. Suppose the tree is given to us like this: A, B, C, then you have D, then you have E. Okay, 1, 2, 3, 4, and 5. Then you have A, B, C, F, and G, and 6 and 7. Now let's represent this into the array. 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5, 6, and 7. So we have A, B, C, D, and E. Two blank spaces are there because we don't have the left and right child of C. And we will make the insertion. If we want to append any alphabet, then we can append it with C. So this is your complete binary tree. Complete binary tree. See, no missing values. I show you one thing more, then I'll tell you how to differentiate. 1, 2, 3, 4, 5, 6, and 7. A, B, C. Now you can apparently differentiate between two. The differentiation is apparent that in the figure A, this is figure B. In figure A, you have blank spaces at the end. That means you have the room to append the or to insert the alphabets with C. Here, the missing values are in between the array. That is 4 and 5 are missing, 6 and 7 are filled. So this is not a complete binary. Not a complete binary. So this is not a complete binary tree, and this is the complete binary tree where either all the levels are filled or the spaces are left in the end, then it is a complete binary tree. If the spaces are lying in between, then this is not a complete binary tree. Okay. So what would be the height of a complete binary tree? Just gone. How many levels are there? 1, 2, and 3. How many levels are there? 1, 2, and 3 levels are there. Now, what would be the number of nodes? What would be the number of nodes that this tree would have? That is 2 raised to power number of levels, that is 3 minus 1. So it could be 8 minus 1, which is 7. If I count 1, 2, 3, 4, 5, 6, 7 nodes are there. Okay. How many nodes are there? 2 raised to power level minus 1. 2 raised to power number of levels. 2 raised to power number of levels minus 1. That is called 8 minus 7. Okay. Now, if I represent the tree in this format, A, B, C, D, E, F, and G. 1, 2, 3, 4, 5, 6, and 7. So when there is no room, when there is no space to add more values, that is called full binary tree. No spaces, no missing values in the array so that we can add more numbers or more values, then it is called full binary tree. It is called full binary tree because array representation is full with the 7 nodes. So this is called full binary tree. Okay. Okay, next. Sometimes we say a full binary tree is also a complete binary tree. In some cases, we also say full binary tree is also complete binary tree, because in this, each node is having at most 2 children. So this is full binary tree is also a complete binary tree. Full binary tree is also a complete binary tree. So next, what would be the height of the binary tree? It is always given in the form of levels, that is in log n. Since I have told you this is n, it is divided into 2 levels, n by 2. Then it is divided by n by 4 levels. See how many nodes? 1, 2, 3, 4. Again, it will be divided into n by 8. So this is how it will be broken up. So this is given by log n level. So it is given by log n level. When we are dividing the tree in this form, it is given by log n levels. Okay. Okay. Now we will add the nodes. Then we will create the max heap and min heap. So max heap where the root node is greater than its descendants. Suppose this is index 1, this is my parent node. See, the value at parent node, root node 1, is greater than 2 and 3. Value at 2 node is greater than 4 and 5. Value at 3 is greater than 6 and 7. So this is called max heap, where root value of root node, value of parent node is greater than both the descendants. Both the descendants. So this is also called decreasing order, descending order or decreasing order heap. 50, 30, 20, then comes 24, 25. Just wait. It will come as 24, 28, 24, then 20, then 10, then 5. When you will remove the elements, I will tell you how to remove the elements. Then they will come in the decreasing order in max heap. Fine. This is just the output which I am showing you, but I'll tell you how to get these elements one by one. And min heap is the heap where the parent node is smaller than both of its descendant. Now, if I change like this, I'll change it. Suppose there is 10. Now you see, value at the parent node is less than its leaf node. 60 is less than 65 and 69. 70 is less than 73 and 75. 40 is less than 60 and 70, and this total heap satisfy the min heap property. This is called min heap. This is called min heap property, where the parent node is smaller than both of its descendants. Then it is called min heap property. Then it is called min heap. What does it called? It is called min heap property. Now, if we are given a tree, how we will insert the element? Inserting the element in a tree, in a heap, in a max heap. How to insert the element? For example, we have been given this. 50, 30, 20. Then we will take 15, 10, 8, and 6. Now this is a full binary tree or a complete binary tree which is having all its level full. Suppose I need to insert 60 here. If you see this tree, it is satisfying which property? Max heap. Because at every root node is greater than its child node. 50 is greater than 30 and 20, 30 is greater than 15 and 10, or 20 is greater than 8 and 6. Now I want to insert supposingly 70. And now where should I insert? I will append it to the C. 1, 2, 3, 4, 5, 6, and 7. I want to insert 70. So 4's left child would be 4 into 2, that is 8. So insert at 8th position 70. Okay. Now you see this element 70 is not satisfying the max heap property. It is not satisfying the max heap property. So in order to satisfy the max heap property, what we are supposed to do? We have to swap this value. If the parent is smaller than the leaf node, then we are going to exchange these values. 70 is smaller, 15, parent is smaller, that is 8's parent is 4, and 15 is smaller than 70. So we are going to swap it. So this will become 15, this will become 70. Okay. Now you again see whether it is satisfying max heap property. No, since 70 is bigger than 30. Fine. And you will swap 30 with 70 because 30 is smaller than 70. Now you put this way 70, 30, and 15. Now again, compare 50 with 70 and 20, which is greater 70. 70 is again greater than its parent. So swap these values. This becomes 50 and this becomes 70. So this is how you will insert the element and satisfy the max heap property. Just swap. If you find the parent and left value has to be swapped. Supposingly, I want to add one more value. I tell you how to add it. Because there will be one question in your mind. I will answer that. We have added 70 here. 70 was not satisfying the max heap property because 70 was greater than 15. So 15 was its parent. So we swapped 70 with 15. Then we saw again, it was again not satisfying the max heap property. So 30 came down and 70 goes up at the level 1. Now at the level 2, there was 50 and 50 was smaller than 70. So we have to swap. Fine. Now supposingly there is one more element. Let us take it as 55, which is on the right hand side. Now see, 15 is smaller, 55 is bigger. Now you compare both of these children first, 15 and 55. Now which is greater? 55 is greater than its parent node, that is 30. So swap 30 and 55. 55 will come here and 30 will come here. Now it is again not satisfying the max heap property. Then 55 will go up and 50 will come down. So this is how it satisfies the max heap property. This is how the insertions are done. Okay, this is how the values are inserted. These all techniques will be used while we will be doing the heap sort. We need to form the max heap. We need to form the insertion in max heap, then deletion from the max heap. Then we will be getting the sorted numbers. Okay. Now let's do the deletion part. Suppose this is a tree which is given to us. Now how to delete the element? Delete the element in the max heap. How to do it first? First of all, in max heap, the maximum element, the element which is having the maximum value, it lies at the root. It lies at the root. Maximum value number will lie at the root. So remove it. So 70 will come out. 70 will come out. Okay. Now you just remove this. It is blank now. Now what to replace it with? The right child, the first child, the right child of node number 3 will go here. It will come here. Okay. Now you have inserted there, just remove it. Now you see whether it is satisfying the max heapify it. Heapify means to check whether it is satisfying max heap property or not. Whether it is satisfying max heap property or not. Now you see 6 is smaller than 55 and 20. Which is greater? 55. So 6 will come here and 55 will move up. 55 will move up and 6 will come down. Now you see 50 and 10. Both the descendants of 6 are greater than it. Okay. Which is greatest? 50 is the greater number. So bring 6 down and 50 will move up. And 50 will move up. Now you see the tree is satisfying the max heap property. 55, 50 and 20 are smaller than 55. Then 6 and 10 are smaller than 50, whereas 8 is also smaller than 20. Now 55 is to be removed. So first number was 70, then comes 55. It will be stored in the last location and location before it will have 55. So remove 55 and substitute this number, swap this number here, put here. So this has gone. You have taken the second largest number out of this heap. Now it is not again satisfying the max heap property. See, 20 and 50 are both greater than 8. So let's do once again. 50 will come here. 8 will come here. Now, what happens? Six and 10. 10 is greater than 6. Fine. Then means 8 will be replaced by 10 and 8 will come here. 8 will become the right child of 10. Now you can see it is satisfying the max heap property. 50, 10, 20, 6 and 8. Okay, fine. This is how it is being done. We will do it one by one. See, this is the number 6 and it is to be deleted. Sorry. The first element is root is at first location and the value, the maximum value resides in the root element in the maximum. The value which is maximum, it resides in the root element in the maximum, and that is at location 1. So when we are going to remove this, deletions will be made from this root only. So first entry which number will come out is 50. Now you have to replace this number with the right child, or if it is having one child, then you can replace it with the left child. So this is your first child, that is right child, 7 number child. So put 6 here. Once it is here, just remove it. Now 20 is having only one left child, that is 8. Now you see this tree, it is not satisfying the max heap property. This tree is not satisfying the max heap property. Now how we will do it? For that, what we will do, check 6 is at the root element and 30 and 20 are its descendants. 30 and 20 are its descendants. Which is greater? 30 number. So replace or swap 30 with the 6. Swap 30 with 6. Now you see 6 is having two descendants, 15 and 10, and it is smaller than both of them. Now out of 4 and 5, that is 15 and 10, which is greater? 15. So we are going to swap 66 with 15. So 15 will come here and 6 will come down. So now you see this tree is satisfying the max heap property. That is the root element of every leaf node. The root of every leaf node is greater than its child node. Now you see, okay. Now I want to replace 30. 30 will come out. It is the second largest number in the tree. So this will come out. Replace this number with 8. This is the leftover child. So take it here. Replace this number with 8. So 8 will come here. 30 has gone out. Okay. Now what happens? 8 is greater than 50. 8 is smaller than 15 and 20. So it is violating max heap property. Violating max heap property. So we have to heapify it. Heapify it. That means you have to select which number is greater. 20 is greater. So replace 8 with the 20. So 20 will come here and 8 will go down. This is how it is done. Now you see the third largest number in the heap is 20. So 20 will go out. Replace 20 with this number, that is 8. So this tree has gone, right tree has gone now. This number is 8. Now this tree is again violating the max heap property. So how you will be satisfying it? 8 will be replaced or swapped by 15 and 8 will come here. Now 6 and 10, which is greater? 10. So 10 will replace 8. Now you see this is satisfying the heap property. Then 15 will come out. 15 will come out, and how it will be replaced? It will be replaced by 8. Come here. This is 8. Now you see 8, 10 and 6. So 8 is greater than 10. It is violating max heap property. So swap this number with this. 10 will come here. 8 will go down. Now you see 10 left child is 8. 8's left child is 6. And they are all satisfying the heap property. Now 10 will go out. If you see, it is the fifth largest number. So 10 will go out. Just wait. 10 will go out and 6 will replace 10. 6 will replace 10. Now it is not satisfying the max heap property. So 8 will go up and 6 will come down. 8 will go up and 6 will come down. Now remove 8. So this 8 will be replaced by 6 itself. So last number would be 6. Hence, we will get the sorted list in this manner. Hence, we will get the sorted list in this manner. So the binary heap data structure is an array that can be viewed as a complete binary tree. So each node of binary tree corresponds to the element in an array, and array is completely filled on all the levels except possibly the lowest level. So the root of the tree A1 and the given index I of the node, the indices of its parent, left child and right child can be computed as parent will be at I. So return the floor value of I by 2. Left of I is 2 into I and right of I is 2 into I plus 1. So how for every node V other than the root, the key stored in V is greater than or equal to than the key stored in the parent. I told you the value at the parent should be greater than or equal to the value at its descendant. Otherwise, the maximum value is stored in the root node only. So maxif, I told you, store the data in the ascending order and has the property where every parent is greater than its root node. Min heap where every parent is smaller than its root node. So this is a max heap example. As you can see, the nodes are having the greater value than their descendants. 19 is the parent node, root node of the tree, which is greater than 12 and 16. 12 is greater than 1 and 4, and 16 is greater than 7. So min heap where every value is smaller. Okay. I'll show. So heap data structure is a binary tree with the following two properties. It is a complete binary tree. Each level of tree is completely filled except possibly the bottom level. Fine. The last level can be incomplete, but the other levels are completely filled. And this level should be filled from left to right. As you can see, A, B, C, D, E, F is a where the pink pink highlighting is there. It is a binary tree because it is not having the left child. When you put F as a left child, then it becomes the complete binary tree, or it becomes the heap, because here the child are filled from left to right. So it satisfies the heap order property that the data item stored in each node is greater than or equal to the data item which is stored in the children. I told you already that the data at the parent node should be greater than its child node. So C7 child is 8 and it does not satisfy the heap property. And if we reverse it, 8's child should be 7, then it is a heap. As you can see, 9 child is 6 and 7, and 7 child is 1. 6 children are 2 and 4. So they are satisfying the heap property. So I told you how to represent it in the form of array. See, 16, 14, 10, these are all children. They are, numbered from 1 to 10. So for I is equal to 4. 4 is a parent. 4's parent is 2 because parent lives at I by 2 position. So it is 2. Left child would be 8 and right child would be 9. See, left child would be 8 and right child would be 9. This is how it is done. Types of heap, we can check. Where the value of root node is greater than or equal to the children node, then it is a max heap. Where the root node is smaller or less than equal to children node, then it is a min heap. So these are the three processes which are used in creating the heap sort. So this is the algo. First, complete the build the complete binary tree using the given elements. Whatever the elements are given to you, build the complete binary tree. Then perform the max heap heapification in order to convert that into the ascending order. Once the heap is created, swap the last node with the root node and delete it from the heap. And repeat steps 2 and 3 until the heap is empty. That we have done already on the board. So this is the elements which are sorted. Sort the following elements in the ascending order. First of all, we have to build the heap. See, I tell you, first of all, 4 will be there, then 10, then 3, then 5, then 1. This is how the nodes, a binary tree is, the array is being converted into the binary tree, or binary tree. From that, we have to convert it into heap. In max heap, we have to check whether the parent node is greater than or equal to. So see how it is done. 10 is greater than 4. Then 10 will replace 4 and 4 will come down. So swap 10 and 4. Now from children of 4, 5 is greater. So swap 5 and 4. So it is swapping. So this is how it is swapped. Now you see the numbers are in the ascending order. Now we have to delete. So get 10 out, 10, 5. So max heap is built because every number at the root node is greater than its children node. Now how to perform the deletion? So take 10 out and swap last node with the root node. So 10 node will be removed. 1, 5, 3, 4 are left. Now you see it is not satisfying the heapification property. Now you 5 and 3, which is greater? 5 is greater, so swap 5 and 1. Then 1 is smaller than 4, so swap 4 and 1. Now you see it satisfies the max heap property. So 10, which is indicated in red, that means this is the sorted element and it would be the last element in the array. So max heap is built. Now step 3. Remove the last change, replace the last node with the first node. And 5 has gone. 5 has come to its required position. Now 4 will replace 1 as in order to satisfy the heap property. So 4 is replacing 1. Then 3 is replacing 4 because last node has to be out. So now 4 is there and delete 4. Now 3 will be deleted. Sorry, 1 will be replaced with 3 and 3 will be deleted. Then you are left with 1. This is how the sorting is over. How to create a max heap? First of all, you will arrange all the numbers into the array. Whatever is given in the unsorted form only, you will arrange these numbers in the array. Give the indexes 1, 2, 3, 4, 5, and 6. Okay. First number is 40. I'm taking step by step. So take 40 as it is. Second number is 10. So 40 is greater than 10 and it is its left child. Okay. Now 50 is at 3. This is step number 2. Now at 3 we have 40, then 10, then 50. Either you heapify it here or I have shown you the PPT, you can heapify there. So we can heapify since 10 and 50 are there. So 40 is smaller than 50 and 50 is also greater than 10. So swap 50 and 40. 50 and 40. Okay. Now 30 number is there. 30 is at position number 4. So it is left child of node number 2. So it is step number 4. Now you can see it is again violating the max heap property. So 30 is greater than 10. Fine. So I will swap 10 and 30. I will swap 10 and 30. So 10 will come in place of 30 and 30 will go in place of 10. Now you see 30 is smaller than 50. Yes. 40 is smaller than 50. Yes, it is okay. Now next is 20. So 20 is there. So if it is satisfying the heap property, place it where it is to be. Otherwise, find its appropriate location and then place. Now 60. So 60 is here. It is the left child of node number 3. Now what we are supposed to do, since from the entire tree, this is only violating the max heap property. So swap 60 and 40. At every step, you have to perform the heapification. Now you see, there is 50, there is 30, and there is 60. Now 60 is greater than 50, but 30 is smaller. So root element should be greater than all the numbers which are there in a tree. So swap it, 60 and 50 will come here. This is how the max heap is created using these numbers. And deletion, I've already told you how to delete it, that we can do and perform the sorting. So for this, we have 3 algos that I will be writing. Then we will be doing the time complexity of this. Just wait. First of all, we will write the max CP5 algo because it is used in all the three. One. I will tell you the working of this, then we will move to other algos. A, N, and I, integer largest is equal to I, left child is equal to 2 into I, right child is equal to 2 into I plus 1. Then while L is less than equal to N, that is number of elements in an array, and A of L is greater than largest, then largest is equal to L. While R is less than equal to N and A of R is greater than A of largest, then largest is equal to R. If largest is not equal to I, then swap A largest with AI. Then perform heapification. Heapify A comma N comma largest, then close this. This is the algo, and we will try to make it out. So this is the tree which is given to me: 50, 30, 20, 15, 10, 8, and 6. Okay. So how will this algo work? We have to take first this tree into the consideration, that is 20, 8, and 6. Okay. 28 and 6. Now I tell you largest is equal to I. So this will say largest is equal to I because this is my root node of this particular tree. Left child is 8 and right child is 6 because this is our index number 6 and 7. Fine. So while L is less than equal to N. So L is 6 and total nodes are 7. So 6 is less than N, condition is true. And A of L, that is A of 6 is greater than largest. If A of 6, supposingly this is 8, this is 20, if I'm talking about it. Supposingly trees like this, 8, 20, and 6. Initially store I as largest, that is 8. Now A6 is greater than largest, 20 is greater than 8, yes, then largest is equal to L. Largest would be equal to 20. Now on the other side, while R is less than equal to N, 7 is less than equal to 7, condition is true, and A of R is greater than 6 is greater than 8. No. Condition false. So this loop will not execute. Now you have to check if largest is not equal to I, because largest is not equal to I. We said I is largest is equal to 20, but 20 is not equal to 8. So swap A largest with AI. So we are going to swap these. This is going to become 20 and this is going to become 8. Then heapify AN with the largest. A means array of elements till the type total given, and the largest would be the largest element, that is 20 from here, with the other elements in the tree. Supposingly this is a tree. So I'm taking 20, 9 and 30. Largest is equal to I. So this is my largest, 20. Fine, this is at 2, 4 and 5. Now L is less than N, 4 is less than 5, condition true. And A of L is greater than largest. 9 is not greater than largest. So this condition will not follow. A of L is greater than largest. That is 9 is not greater than largest. That is 20. So this condition falls. So this will not execute. While R is less than equal to N, 5 is less than equal to 5, condition is true. Then AR is greater than 30 is greater than 20. Condition is true. So largest is equal to R, which is equal to 30. So we have stored the 30 in largest variable. Now if largest is not equal to I, means we are saying earlier we assumed that largest is equal to 20. Now we are saying largest is equal to 30. So we are going to replace 30 with 20. So we are going to replace 30 with 20. Okay, so this is how. Then you will again call heapify AN largest. Now this tree has changed to 30, 9 and 20. Okay. Now you again call the heapification on this. How we will call it? 15, 30 and 7. Largest is equal to parent node, that is I, and this condition 2, 3, 1. So total number of elements are 5. 2 is less than 5, condition true. A of L, 15 is greater than largest. 30, no. Just wait. Sorry. A of L, that is A of 2, 30 is greater than 15, condition is true. So largest will be equal to L. Largest will be equal to 30. Now right side will not continue. Largest is not equal to I, because 30 is not equal to 15, because 15 is already, we have mentioned that this is the largest number, and 30 is not the 30 is the largest number, whereas 15 is not. So we are going to swap it. So bring this here, 30, 15 and 7. So this tree has now satisfied the heapify property, that is 30 and 15. Okay. Now you have to again call the, because from here 30 is the largest. Now this again tree has left to me in the non-heapification, means this is not satisfying the heapification property. Now as you can see, left child is not greater than the largest. So right child is greater. So this condition will follow. Largest will be equal to 20. And 20 will swap, because we have assumed largest is equal to I in the beginning. So this is again going to swap. So this will become 20 and this will become 15. And this is how the heapification is done. So this becomes 20. This becomes 15. Now you can see every child is smaller than the descendant child. This is how heapification algorithm works. Thank you, dear students, for this lecture. We have done the core algo. Rest of the part we will be doing in next lecture. So, thank you so much.